Welcome to qnawire.
Okay, so the lowest temperature and the pressure we can get for this case is the critical temperature and the critical pressure. So before we determine the value for the lowest temperature and the pressure, let's do some setup here. So we know the Mach number can be equal to V over C, which is equal to V over square root KRT. And then we know T0 over T is equal to 1 plus K minus 1 over 2 times Mach number squared, which is equal to 1 plus K minus 1 over 2 times V squared over KRT. So therefore, we have T0, which is the stagnation temperature, is equal to T times 1 plus K minus 1 over 2 times V squared over KRT. So we know P0 over P is equal to 1 plus K minus 1 over 2, and then times MA to the power 2 to the power of K over K minus 1, which is equal to 1 plus K minus 1 over 2, and then times V squared over KRT to the power of K over K minus 1. So we have P0 is equal to P times 1 plus K minus 1 over 2, and then times V squared over KRT, and then times to the power of K over K minus 1. So therefore, we know the value for the critical temperature, which is the T asterisk, can be determined by such equation here. So we know T asterisk over T0 is equal to 2 over K plus 1. So therefore, T asterisk is equal to 2T0 over K plus 1. So if we do some arrangement here, eventually we have T is equal to the T asterisk, which is the critical temperature here, is equal to 2T times 1 plus K minus 1 over 2 times V squared over KRT, and then over K plus 1. So we know T here is the static temperature, which is given as 800 Kelvin, and the K here is the specific heat ratio for the helium, which is 1.667, and R here is the gas constant for the helium, which is 2.0769 kilojoule per kilogram times Kelvin. If we convert it to joule per kilogram times Kelvin, it's 2076.9 joule kilogram times Kelvin. And we know the velocity is given as 100 meter per second. So therefore, we can determine the value of the lowest temperature, which is the value for the critical temperature. So now let's plug in back to the equation to determine such value. So T asterisk can be equal to 2 times 800 Kelvin, and then times 1 plus 1.667 minus 1 divided by 2, and then times 100 meter per second square over 1.667, and then times 2076.9 kilojoule. I'm sorry, not kilojoule, joule per kilogram times Kelvin, and then times 800 Kelvin. And this whole thing here over 1.667 plus 1. And this will give us the lowest temperature we can get is about 601 Kelvin. So now let's determine the lowest pressure, which is the value for the critical pressure, which can be equal to P times 1 plus K minus 1 over 2 times V squared. And then, you know what, let me make some adjustment here. Okay, so this is the correct equation for the critical pressure, okay? So now we know the pressure is given as 0.77 megapascal. So now let's plug in back to the equation to determine the lowest pressure value, which is the value for the critical pressure, which can be equal to 0.7 megapascal times 1 plus 1.667 minus 1 divided by 2, and then times 100 meter per second to the power 2 over 1.667 times 2076.9 kilojoule. It's a joule, okay? Because we already converted it from kilojoule, so it's joule per kilogram times Kelvin. And then times 800 Kelvin. And then to the power of 1.667 over 1.667 minus 1. And then multiply by 2 over 1.667 plus 1, and then to the power of 1.667 over 1.667 minus 1. And this will give us the value for the lowest pressure, which is the value for the critical pressure, is about 0.342 megapascal. And these are the answers for this question.